we discussed about these Gromov-Witten invariants last time. Just one more time, because now it's being recorded. Then we are going to n-pointed Gromov-Witten invariant. The argument is that the classes alpha i's could be P2, line, or P point, basically, or the subspace of P2. And then also, giving the degree axiom, we have this restriction on the sum of the degree of alpha i's. Okay? So, okay, we know that here sum of the degree of alpha I from 1 to n is going to be 4 plus 6 times d minus 6 plus n. So this would be 6d minus 2 plus 2n. Basically, that calculation, you know, this 6, where is that coming from? I guess at least some of it you can see basically, right? So dimension of x is 2, genus is 0, so that is the 4, and then this is the degree minus 3 class, so that's where your 6 times this term here, right? 6 times t, this is minus 3. So this is a hypersurface, right? It's the canonical surface. So this is P2. And inside P2 is the anti-canonical divisor, meaning that associated to this, there is this degree 3 surface inside P2. So that is your anti-canonical divisor. Okay. And then this thing is being integrated, class of it is being integrated against class of beta, and that's times d times class of line. So if you have a line, how many times does it go through this? Of course, a line in P2 is not necessarily just a straight line, so it is like that. And then that will be basically this degree here, 3 times d times 2, but minus 3 times d times 2. And that's the 6 times d. There you go. So this is basically minus 2 times canonical of x over d times class of L. So that makes sense. And then 2 times 3g minus 3 plus n also. So that's the genus is 0. So that's your other number. That's it. So it's easy to calculate. Yeah. So for n equal to 0 and 1, this equation does not have a solution, right? Does not have a solution. Let's just see if it is n equals series. So it's 4 plus 60 minus. So it is 60 minus 2. Right.
Shouldn't this be n in the degree?
In the degree, actually. Yeah.
And above that, I'm sorry, in the degree equation, in the middle equality, shouldn't this be minus 6 plus 2n, right?
Minus 6 plus 2n. Yes, you're right. And then, yep. Okay. All right. Yes, for n equal to 2 and 3, one checks that. Excellent, very good, thanks. One checks that I0, 2, 1 of, if it has only 2 mark points, and if I have these 2 point classes I put in here, it would be the same as I0, 3, 1. Now pay attention how beautiful this is. If I put this 2 points in here, I can relate that to the 3-pointed curve class. When you know what I should put in here, I can add this extra class, but I would like the sum of the degrees of what I'm putting in here to be equal to the sum of the degrees of this. What is that space whose codimension is 0? So that its degree in cohomology is equal to 0, right? So I can do that. codimension 1. So, okay, so I can put this in here. And we will see that this is equal to 1. All right, so we can actually see that this calculation works. In fact, by reduction axiom, so you calculate the dimension in here and you calculate the degree, sum of the degrees in here, and you can do an analysis and you will see the two match. We can, in fact, by reduction axiom, recall that I, G, and beta, alpha, then alpha 1 all the way to alpha n minus 1, then alpha n, this thing, is equal to B. We did this thing, right? If I want to spit out this part of it, take it out, then that's a cohomology Poincare dual of some cycle. So that's basically Poincare dual of cycles. And then if I want to write the integral in terms of the remaining classes, then I just need to see how many choices I would have for integrating alpha n against the curve class. So that will be integral of alpha n against the curve class times invariant I will get by Gn minus 1 beta of alpha 1 to alpha n minus 1. And this is exactly that calculation. You see, if I put this in here, d is equal to 1, and then it makes sense to, that's why this works out. Okay. All right. So that's that. Now, if n is bigger than equal to 4, then I0 and d of alpha 1 to alpha n turns out to be equal to 0 if some alpha I is equal to class of P2, the whole class of P2, and that is by fundamental class axiom. Okay. Similarly, for n bigger than equal to 4, if alpha n is equal to class of the line, the last one is the line class, then the divisor axiom, you see, as I remember, and you remember, I said that these axioms of Gromov-Witten classes allows you to establish the calculus of computing Gromov-Witten invariants. So then the divisor axiom, then the divisor axiom shows that I, 0, and d of alpha 1 to alpha n minus 1 and L is going to be equal to d, right, times I, 0, n minus 1 d of alpha 1 alpha. If you look at your divisor axiom statement from last time, you will see that this is the case. This L is a divisor inside P2. So that's why, again, when you calculate, if it's a degree D divisor and you're intersecting it with genus 0 curve, that's a line, by Bezout theorem, you will actually see they would have to have D points of intersection, and that's exactly that intersection. Okay, we can proceed inductively this way. Each time I can choose the last one to be the class of a divisor, and I can keep going down and relate Gromov-Witten invariants for n mark points to n minus 1, n minus 2, and so on and so forth. So we can proceed inductively, and eventually we need to, until it makes sense, right? We need to compute eventually we need to compute I, 0, 3D minus 1D of bunch of point classes. When there is a restriction, right, on the number of classes that you see, and the degree axiom tells you, so there should be 3D minus 1 of these things actually for D bigger than or equal to 1. You keep going like that. And this is because degree, by the way, of a point class inside P2, what is it? Complex codimension of a point in P2 is 2. So the real codimension of it is 4. So its degree as a cohomology class in real cohomology class is 4. Yes. And then actually this tells you that you will be ending up with n equal to 3D minus 1, many of these things eventually. And you keep going from up there to here, eventually you end up with that. Each time that you put a class of a P2, you will get something like 0. Each time you get a class of a line, you can relate it to 1 degree less, and then you're left with class of the point. So this is why I'm saying we can proceed inductively and then compute eventually this class. Basically, this is the last element of the computation, because either your alpha is point class or line class or class of the P2. So it boils down to that. And this number, by the way, let's call it something. So n of D, I'm going to define it as the Gromov-Witten invariant of 0, 3D minus 1 marked curves of degree D with class point all the way to point, like that, 3D minus 1 of these things, or D bigger than 1. So this is ND. And what is the ND? ND gives the number of rational curves. They are genus 0, right? Rational curves are what degree? Rational curves of degree D in P2 passing through 3D minus 1 points. As clear as it can be based on that definition. Okay. Now here is a remark. If you search the literature, you will realize that ND is also degree of Savary variety of degree D. Search the literature and try to fulfill your curiosity, and then you will see it has the same definition. Now, okay, so Gromov-Witten invariance of genus 0 curves in P2 eventually allows us to calculate the number of rational curves passing through, of degree D passing through 3D minus 1 points. And the 3D minus 1 really comes because of the degree axiom. That's what we are forced to eventually be computing. Now here is the beautiful proposition in this particular example. Here's a proposition. So see now, similar to the whiteboard, I can change the color, and that's beautiful. Okay, proposition. There is a recursion formula. This is one of the most important propositions. There's a recursion formula for NDs. So if you remember, I told you that often there is no relationship between Gromov-Witten invariance. Sometimes there is, sometimes there's not. Often, though, there isn't. But this one is not one of those cases. This is the one that actually does have a relation. So ND is going to be a sum over D equal to D1 plus D2. D1 and D2 both need to be bigger than 0 integers. N of D1 times N of D2 times d1 squared times d2 squared times the choice of 3d1 minus 2 points out of 3d minus 4 points minus d1 cubed times d2 times 3d1 minus 1, 3d minus 1 choices. And this whole thing is inside a big bracket. Okay, so if you break the number of the degree of the curve into d1, d2, such that they add up to d, as long as each degree is bigger than 0, then there's a relation between the Gromov-Witten invariants of curves of degree d1 and d2 and original curve of degree d. Okay, so now you can see how beautiful this is. Doing Gromov-Witten invariants, you can, in theory, you can actually relate the degree of the Savary varieties of degree d curves and degree d1 and d2. Okay, so n1, by the way, is equal to I0, 2, 1, yes, point. So this is the thing that we actually calculated. That is 1, and n3 is going to be 12, n4 is going to be 620, n5 is going to be 87,304. Okay, and this is beautiful. I mean, you can calculate these numbers, yes, and so on and so forth. Okay, now here is the proof of the statement. So let us define a parameter. So let us define C to be equal to I0 3D. So 3D pointed curves of degree D, where the class is going to be a sequence of classes, point classes like this. And then the last two I pick to be line classes. And this is the Gromov-Witten class. So it belongs to cohomology theory of the moduli space compactification of moduli space of genus 0 3D pointed curves with rational coefficients. Now we know where the Gromov-Witten class lives at. So by degree axiom, this is the class of degree. Oh wait, so this is a class of degree, so 2 times dimension over complex numbers of m bar 0 3D minus 2. So its intersection with a divisor is well defined. Well-defined rational number. Okay, what's happening? You calculate the degree, okay, by degree axiom. Then you realize that the Gromov-Witten class will have this degree. It's working over real dimensions. So this is the degree over reals. If I divide by 2, it's the complex dimension of the moduli space minus 1. So it's a divisor class. So in the moduli space of genus 0 3D curves, okay, I'm picking a divisor in that moduli space. And those curves, after being embedded into the ambient variety, pass through these configurations of points and lines. So this basically cuts out the locus of a divisor inside that moduli. So it's a divisor class. Therefore, because it's codimension 1, I can integrate it or I can intersect it with the divisor. And I will get a well-defined number, rational number. And I get a rational number because this cohomology class is having coefficients in field of rational numbers. Okay, so this is what it is. We need a suitable divisor. Let's call this divisor D in this moduli space, 0, 3D, to compute this number. Compute this number. Okay. So how do we choose this divisor? So this is trying to explain this suitable divisor. So I put the semicolon here. So fix a partition. Fix a partition of indexed 3D mark points. So I'm going to choose these divisors by looking at partitioning of the mark points. 3D mark points on a stable curve. On a stable curve in M bar 0 3D, basically, by the set. So I'm going to use it this way. I equal to 1, 2. So it's going to be all the way to 3D minus 4, and then PQRS. Okay, do you remember what we were doing? We were looking, if you remember, we were looking at M bar 0, 3, remember? That was just a single point. And then we were looking at M bar 0, 4, and that was a P1. And it was a P1 with 3 special canonical points on it. Each time I picked a point in this P1, I looked at the tree of curves. And so something like that, and something like that. I had 1, 2, 3, 4. I had 1, 3, 2, 4. And I had 1, 4, 2, 3, something like that, right? Each one was a divisor in P1. And because the moduli space M bar 0, 4 was a P1, each choice of partitioning the 4 points gave me a divisor. Yeah. So then we said we can go all the way up M bar 0 n. And in order to basically pick the divisors, we argued that if I can split n to n minus 4 and 4 points, then choice of labeling of these 4 points, similar to this situation in here, gives me divisors, right? All I need to make sure is that these 1, 2, 3, 4 need to sit inside configurations of reduced curve like that, such that we call this A, and we call this one B, and so on and so forth. And A needed to include the labeling, so 1, 2, and B needed to include the 3, 4, and so on and so forth. So we said that we can actually do this. And if we keep going up in M bar 0 n, we keep getting those divisors we want by looking at partitioning of these 4 points. So we made sure that P and Q belonged in the partition A, and R and S belonged in partition B, and so on and so forth. So all possible ways that you can pick it, the partition. Yes. So if you remember this thing now, you can actually see that it's coming back to us. So we would like to calculate integral of the Gromov-Witten class. We realize that the Gromov-Witten class is complex codimension 1. It's a divisor class. And inside this M bar 0 3D, I'm going to pick those divisors. And I know how to do it. I will split 3D points into 4 points and 3D minus 4 points and play that game I played before. Okay, so this is exactly that. So this means that C will have the property that alpha 1 is going to be equal to alpha 2 equal to all the way to alpha 3d minus 4, right? To alpha p equal to alpha q as point classes. And the last 2 points, remember? So it's true that these two points are part of, I have PQRS. The choice of partitioning, basically, how many ways I can put PQ inside A or RS inside B, or PR in A, QS in B, or PS in A, QR in B, and so on. These give you divisors, right? But we are calculating this particular number, remember. So rest of the points can be attached to the points in P2, but 2 of these points out of even our partition needs to stay on 2 lines. So last 2, alpha R and alpha S, are going to be line classes. That's the invariant I'm trying to calculate. Essentially, pictorially, these 2 guys need to be passing through some kind of a lines in P2. So this is line 1 and this is line 2. Okay, beautiful picture, right? Okay, so that's that. Now, partition this set I, this set, index set into disjoint sets A and B, exactly as before, as in splitting axiom. This gives a natural map from, let's call this natural map, which is depending on the choice of partition A, B. So it's going to be a map from M bar 0 cardinality. This is the cardinality of set A of A plus 1 times M bar 0 cardinality of B plus 1, okay, to M bar 0 3D. Yes, so in a splitting axiom, we actually saw that we can do this. We can split the point configurations, but then we have this point, extra point in here, and we have this extra point in here. And when they land in here, there need to be compatibility, meaning if I'm picking point P and Q, image of the map after being embedded into the ambient space should have the condition that f of P and f of Q need to be equal to each other. So this was that part that we had this diagonal sitting in the cohomology theory last time. So the image of phi of AB is a divisor in M bar 0 3D. Yes, this does make sense to you. Why? Because I have partitioned 3D points. Partition is given by A and B, and A has 2 of them, and B has 2 other ones. And these PQRS are the 4 ones that give me the divisors. That makes sense. Image is going to be gluing these 2 split curves, this one and this one. After gluing will be something like that. And the image has that property of the partition. So, okay, after identifying this extra point in here and this extra point in here, we get what we want. Okay, furthermore, the fundamental linear equivalence of divisors tells us that Well, if you remember, as points in P1, these 3 points are linearly equivalent. So when we went this ladder of hierarchy up and up and up, and we were looking at m bar 0 n, we said that all those divisors that we get from different partitioning of PQ, putting it in A and B, or PQ in B and the others, so forth, these give us linearly equivalent divisors. We had this thing before. So this what actually tells us that the possible sum of R of S, R and S in A and PQ in B of image of phi A and B, image of phi A B in here is the divisor. So image of phi A B in here is sitting as a divisor. So now, depending on how you choose this divisor, the whole sum of such partitions is going to be linearly equivalent as in Chow, because I even asked you guys, what does it mean adding? Because these are divisors, I'm looking at the codimension 1 part of the Chow homology, right? Chow group. And as divisors, I can add them. So Q and S is in B, yes. And then this is image of phi AB. So these are all linearly equivalent divisors. Okay, so here's a reminder. This follows because phi from m bar 0 3D to m bar 0 4, remember it's all fibered over m bar 0 4, which forgets 3D minus 4 points and contracts the unstable components. We discussed about this thing. If you forget, even inside the moduli space, there is no x in here. The reason we are not discussing x is that this is a discussion about the Gromov-Witten class itself. It's true that integral of the Gromov-Witten class can be realized as an integral on the stable map moduli space, but that's not what we are doing. We are calculating that integral as an integral of Gromov-Witten class over the stable curve moduli space. Okay, so stable curve moduli space had this property that on the interior, if I forget whatever number of points, I can just land on the interior there, no problem. But on the boundary, I have the notion of stability for the curves. So if I forget 3D minus 4 points, some of those irreducible components of normalization of our curves will become unstable. So I need to collapse them to points. Otherwise, I don't land on something permissible or allowable. So the unstable components under this map, and so this follows because this map, which forgets the points and contracts the unstable component, tells us that under this map, image, so RS in A, sum of RS in A and PQ in B of the image of phi of A comma B is the fiber of phi, yeah, over the stable curve PQRS, basically. And it's a point in m bar 04. You remember that. M bar 04 is P1, yeah? So this was isomorphic to P1. Why is it isomorphic to P1? We can always recover and regenerate all of the things that we learned in this class, because if it were only 3 points, that's a P1 with 3 canonical points. Up to automorphisms, that's just a single point. If it is P1 with 4 points on it, the last point has to be distinct from the other 3 points. But up to linear equivalence, it has to be distinct from 0, 1, infinity of P1. So it has a choice of the whole P1 for itself to land wherever they want. Yeah. So similarly, summing over PQ, PR in A and QS in B of image of phi AB is fiber of phi. Well, now you kind of know what over what point over, okay, what is it, PR and Q and S, right? As easy as that. Yeah. Okay, so that's that. We know that M bar 0, 4 is isomorphic to P1 minus its 3 canonical points, and the above stable curve is one of the 3 points in P1. Yeah. Since the points, i.e. divisors above are linearly equivalent in P1, then we get that the fibers also divisors, so I call this a star, the fiber RS in A and PQ in B of the image of phi AB is going to be linearly, okay, so this is a bad notation. Yeah, this way. Linearly equivalent to image of phi AB when PR is in A and QS is in. Okay. So this we discussed, but I just thought maybe I can spell it out again. Spending time sometimes is good because, you know, it reviews for us the content. Yeah. Now we can intersect C. What is C? It was this Gromov-Witten class. It's a codimension 1 cohomology class. It's a divisor class. And we have complete control on what the divisors in M bar 0, 3D are. They are given by fibers of M bar 0, 3D over M bar 0, 4 over the points that give us these configurations. Okay. So now we can intersect. Let's intersect sigma with those divisors, with divisors in star, with the linearly equivalent divisor in the star. So let's do that. Okay. Given phi of A comma B from M bar 0 A plus 1 times M bar 0 B plus 1 to M bar 0 3D, yes, and the divisor associated to partitioning A, B, which is the sum RS in A, PQ in B, for instance, of image of phi AB, then C intersected with AB with this divisor is given by, see how beautiful everything that we learned about Gromov-Witten axioms is going to help us in here. You see, this intersection now is going to be given by phi AB upper star of C, right? Which we can calculate, by splitting axiom that we had before. Splitting axiom. So what is that going to be? Splitting axiom, recall. So recall. That was basically saying that if I have phi, a map, m bar g, n1 plus 1, and m bar g, n2 plus 1, yes, to m bar gn, and I take some Gromov-Witten class, yes, so phi upper star of I, g, and beta of alpha 1 comma alpha n is going to be given as a double sum. So it's going to be all the ways that you can break the curve, of course, and then all the ways that you can identify these two additional points. So this is going to be Gij times I of G1 and N1 plus 1 and curve class beta 1 of alpha 1 to alpha N1 and then additional point Ti. Yes. Additional point, no, additional class. That point, extra point, need to lie somewhere. And this Ti is the cohomology class. This is the cohomology class of Poincare dual of cohomology class of that locus where the additional point lies. Yes? And then it's tensored with the other Gromov-Witten class, Ig2 N2 plus 1, yes, beta 2 of, well, alpha N1 plus 1 all the way to last point, alpha N, and then Tj, right? And Tj is the last, the other one. Tj is a Poincare dual of the Zj. So this is what we have. Yeah. Okay. So we are gonna use it. So G's are, we are lucky in here. G's are both 0 for us. For us, G's are all equal to 0. Everything is equal to 0. And N1 and N2, so N1 plus N2 is going to be 3D, basically. Yes. And we know what the alphas are. Everything that we have in here is going to be a point class, except the last two which are going to be the line classes. Yes, but then remember, we are adding this additional point, right? So we have now taken 3D minus 3D of these things. We are taking 4 of them out, and then those two, we are having something in here and something in here. This additional point can lie anywhere it wants. So Ti and Tj, if you recall, Ti and Tj were chosen to be basis of cohomology theory of X. So they can in fact also be the class of P2. Those last 2 points that we are adding can lie anywhere. And associated to it, the cohomology class for that point could be point class or the line class or the P2 itself. Yeah. So, okay, so therefore, since the class of diagonal in P2 times P2 is given by why the diagonal? Because you see, this picture tells us that we are looking at the diagonal, right? So where was it? This point is the point, additional point that we have in here. Let's call it, I don't know, R1, and this is R2, these 2 points. So this goes to this, these 2 points are associated to these additional ones in here. So this point can lie on some Ti, and this point is going to be lying on some Tj, but then evaluation of Ti and Tj need to be compatible to each other under the map. So it's like we are choosing Ti and Tj in cohomology theory of P2, but not in P2 times P2, because choosing Ti Tj gives us 2 copies of cohomology of P2, but in the diagonal that sits inside the twofold product of cohomology of P2. So this diagonal class, I'm going to call it delta, is going to be given by point class times P2, class of P2, plus line class times class of the line class, yes, plus class of P2 times point, right? This is the one that we are interested in. These give, this gives the choice of Ti and Tj. Yeah. Okay, so now let's just do this thing. So under this map, the partition AB of this thing, so we are basically, now we recalled what the splitting axiom is. Now I need to just apply it to my Gromov-Witten class. I'm pulling back my Gromov-Witten class. I get a map sum from D1 plus D2. We know why, because D times class of a line is D1 times line plus D2 times line. And this is my beta, and this is my beta 1, and this is my beta 2. Okay. All right. So then what do I get? I will get, let's see. So I will get the, wait, what do I want to get? So I of 0 of A plus 1 D1 alpha I, where I is chosen from the index set A, and the additional point class. Yes, so this is the one that is attached to Ti, times I from 0 and B plus 1 D2. Yes, alpha I is chosen from the index set B. Yes, index B. Then class of P2. Okay, that's it. Yes. Plus, now pay attention. We said this splitting axiom is summing over all possible I's and J's, summing over all possible choices of Ti and Tj, as long as they sit in the diagonal in twofold cohomology of the ambient variety. Diagonal tells me that once I need to pick Ti to be this one, Tj to be class of P2. Once I need to be taking Ti and Tj both class of the line. Once I need to be taking Ti class of P2 and Tj class of the point. You see? So it's true that we are writing many things, but the calculus is very obvious. So, okay, let's just repeat that. 0. So A plus 1, D1, but this time alpha I in A, instead of Ti, I will put class of L times I0 class of B plus 1 and D2 alpha I in B class of line again. We have one last to go. Yes, so that's the last term right here. So plus I0 A plus 1 D1 alpha I is in A, and then class of the P2, yes, plus times, or I guess Yeah, just times is fine. I tensor. Yeah, tensor. Tensor I0 B. This should be tensor 2. This should be tensor 2. I0 B plus 1 D2 alpha I in B class of the point. Okay. If you haven't followed what we have so far, just let me know now. Okay. So that's it. Yes. So this is exactly the splitting axiom. Okay. So now, so as you can see, the calculation will be basically using a splitting axiom. So we are trying to calculate invariant, right? So we were trying to calculate, where is it? We were trying to calculate and recursive. We are trying to show that there is a recursive formula between the number of rational curves that you get this way inside P2. It's a Gromov-Witten invariant calculation. We then realized that we can use the Gromov-Witten class, pull it back into the splitting of curves, and that has all of those are divisor classes. So because it's a divisor class, I can intersect it with these other divisors that we have. And okay, that's no problem. So I am pulling back this divisor, yes, via the splitting axiom right here. Where is it? I'm putting the divisor in here. So this is that, putting it back to here, yes, gives me the pullback of the divisor class. And then I'm integrating it, intersecting it with the divisors that I have on these two things. Okay, so that's what we are getting. Okay, so now consider, so okay, where is it? Consider, essentially we are calculating after let's put it this way, after intersecting with divisors, okay, so how should I say it? Yeah, so you do understand one thing though, I want to say that this Gromov-Witten class here is a divisor class, okay? This Gromov-Witten class here is a divisor class. Fine. Then M bar 03D is generated by these divisors also. As if you remember that I said that this is the result of Sean Keel, that cohomology theory, the degree 1 cohomology theory of M bar 0n is generated by these linearly equivalent divisors, these DAB, okay? So in some sense, we are doing two things in here. We are pulling back C, which is our Gromov-Witten class, happens to be a divisor. And we are pulling back these DABs also. So in the product, we are intersecting them. So two things are being pulled back and then being intersected in the product. Yeah. So essentially, after intersecting with after intersecting pullback of C with pullbacks P upper star of DAB, we will be computing Gromov-Witten invariants I0 A plus 1 D1 D1 alpha I, where I is in A. Let's call this some class gamma, and I0 B plus 1 D2 alpha I and B gamma prime, where gamma and the gamma prime are one of point class, line class, or the class of P2. Okay, so this is basically essentially this formula. All I'm just saying is that look at this formula in here. This tells you how the Gromov-Witten class is pulled back, and then you need to intersect it with this pullback of the DABs, because those generate the whole degree 1 child group up there. And basically, that's how you calculate these invariants. That's why now I can put the brackets in here. After intersecting, I'm getting these brackets, right? Okay, by our condition on partition A, it includes 2 of the points. Which one was it? So A is the one that has R and S in A. R and S are 2 of those 4 points. And those 2 points, we decided to be the ones that lie on the lines, right? So these 2 need to be lying on the line. Okay, so here, this is R and S, last 2. So A has the partition A has, we have alpha R equal to alpha S equal to the line class. Okay, and alpha I equal to the point class otherwise. Okay, so this is very clear. So now degree of alpha i's is going to be 2 times 1 minus g by the degree axiom. 2 times 1 minus g times dimension of x minus 2 times integral of k of x over beta plus 2 times 3g minus 3 plus n. From here, we can see that cardinality of A is going to be 3d1 plus 2 minus 1/2 degree of this class gamma. Gamma is one of the point class or line class or P2, right? Okay, so what do I get from here? Now since A is fixed, this determines D1 and gamma completely, and it simplifies. The formula. Okay, so how does it simplify the formula? You will see it. Okay, you will see how it simplifies the formula. Okay, now assume that cardinality of A and B are both bigger than or equal to 3, then the fundamental class axiom implies that this invariant I0 A plus 1 D1 alpha i's, where I is in A and we have one class of P2 here, is going to be equal to I0 B plus 1 D2 alpha I, such that I is in B, also class of P2. Both of these things are going to be equal to 0. So you see, if you look at the formula, we have these terms, the ones where we have class of P2 in here, and the one that we have class of P2 in here. It says that both of these classes by the fundamental class axiom go away. So all right, so now we are in better shape because I just need to calculate basically that middle term over there. Yeah. Okay, so this is what the simplification is. So that means the non-vanishing term must have gamma equal to the line class in our formulation, which in turn implies that this cardinality of A, which is 3D1 plus 1, is going to be, and cardinality of B is 3D2. 3D2 minus 1, yes, which then reduces the computation to the following: I0 3D1 plus 1 and D1 of point classes, line, and line times I0 3D2 plus 1 D2 point classes, and then 3D2 minus 1 and a class of line. Okay, and by divisor axiom, okay, I'm gonna go a little bit faster here, but this is based on the calculations that we did. And definition of ND, this reduces to basically seeing that D1 cubed times D1 and D2 and D3. This reduces to this number basically. Hence, C times image of VAB is going to be D1 cubed D2 and D1 and D2. That's it, where cardinality of this thing is 3D1 plus 1. Here, D1 is bigger than 0 and D2 is bigger than 0. Okay?
I'm sorry,
all right.
but what is D3 up there?
Yes, this is the degree of these two curves which we split. Yes? So basically, we are calculating the following. You see, we pull back the Gromov-Witten class. It is split as the tensor product of these classes because diagonal needs to be generated by Ti and Tj. Then we know that instead of Ti and Tj, in each one of those terms, I need to be respectively putting one time P point class P2, then line class times line class, then P2 times point. Then fundamental class axiom tells us that these two terms go away. So the only thing that we have to take care of is the line classes. That's it. And so this is the pullback of the Gromov-Witten class, remember. We want to calculate a rational number. At the same time, any m bar 0n, in particular m bar 0 cardinality of A plus 1 and m bar 0 cardinality of B plus 1 are generated by those linearly equivalent divisors. So in order to calculate this invariant, we're pulling back this thing up there. It's given by some class which is tensor product. So this thing in the middle, right here, is given by that. And we are intersecting this thing against those two divisors, right? And that's it. All right. So as we are doing this, then we are doing this calculation. So we know that gamma can only be the point class. We calculated that thing, and we obtained this computation right here.
But what is these three here?
Oh, I'm sorry. That's what you're asking. I'm so sorry. That's what you're asking. I'm sorry. D1, D2. I'm sorry. Yeah.
Okay, thank you.
Oh, yeah. I'm sorry. That was my mistake. Okay. Okay. I think that essentially, let me see. How much more do I have? So essentially, repeating this computation, essentially, repeating this computation gives us the following result. So Xi times image of phi of AB, PR in A, and QS in B is going to be N of D1, D2, N of D1 times N of D2, D1 squared, D2 squared, choice of 3D minus 4 and 3D1 minus 1. Okay, exactly the formula that we actually had before, plus summing ND1, ND2, D1 cubed D2, choice of 3D minus 4, 3D2 minus 1. That's it. D1, D2 bigger than 0. D1, D2 bigger than 0. Okay? All right. And this is basically the formula that we have. So it's a consequence of basically the splitting axiom. All right, fantastic. Any questions?
And to go into the Donaldson-Thomas invariant?
Not so fast. So the next plan is to, oh, you cut your hair. Is that you? I almost didn't recognize you. I see. Okay, great. Next plan is to, by the way, why is it? So he's turned off his microphone. Next plan is to go to small quantum cohomology.
Okay.
Okay, and a small quantum cohomology, which is, we are doing it. We just calculated, what is a small quantum cohomology? You have a variety, if you count genus 0 curves, that's called the small quantum cohomology. And we discussed it. So you're looking at cohomology theory of your variety, and you are basically intersecting these cohomologies. Usual intersection theory gives you a cycle of intersection of the subspaces. Here we are doing quantum intersection, meaning we are weakly intersecting. So I have the two subspaces, but then I'm looking at weak intersection, meaning like a telephone wire from one to the other. So that's all possible curves that you can pass through between the two. Because these curves have quantum invariants, the genus, the number of mark points, we call this notion of weak intersection the quantum intersection. This induces a structure, rather, some kind of a product even between the two subspaces. So I can think of subspaces weakly intersecting this way. And then I can have a weak notion of intersection product this way. And this intersection product exactly sees quantum parameters of the curve that pass through. So this is what intersection really actually. And quantum cohomology is about quantum intersection theory. If the curves that pass through between subspaces are genus 0, we call it small quantum cohomology. If they are higher genus, we call it big quantum cohomology. We are, after this class today, on Wednesday, we will start talking about small quantum cohomology. We might touch on big quantum cohomology, but remember, big quantum cohomology is problematic because all of these things have to do with computation of Gromov-Witten invariants passing through these cycles. And higher genus Gromov-Witten invariants are not computed really. There's a difficult problem. So we could talk mainly about small quantum cohomology. And then we switch to, okay, are we even counting curves correctly? You should have asked this question from me earlier on. The Gromov-Witten classes are classes in cohomology theory of our ambient space with rational coefficients. And so far we are fine. We calculated one as one of our invariants, which was very nice. Later, you will see that because we are counting curves passing through cycles up to automorphism. In the computation of the Gromov-Witten invariant, you will get numbers which are rational numbers, like 1/2, 1/3, 2/3, 2/5, things like that. And that is problematic because would it make sense if I told you I am counting curves and I get some 1/5 as the number? What is it? Is it one curve with an automorphism group of order 5? Or is one curve, is it two curves with automorphism group 10? What is it? Yes, it's not enumerative because it's a rational number. So you need to replace your curves with objects representing curves such that invariant you obtain is an integer value invariant. And that's the Donaldson-Thomas. So underlying this infinite sequence of Gromov-Witten numbers, there is an underlying infinite sequence of Donaldson-Thomas numbers. And those are integer values. Okay, that's why we are calculating Donaldson-Thomas numbers. Now, when we later discuss Donaldson-Thomas theory, similar to Gromov-Witten numbers, all of these counting invariants are defined as intersection numbers over a moduli space. Donaldson-Thomas invariants are also certain integral over a certain moduli space. Moduli space of sheaves. Now, this moduli space we are interested in relation to Gromov-Witten theory, is the moduli space that parameterizes functions vanishing along curves, ideal sheaves, basically. That moduli space has a very nice name and a very classical object. It's Hilbert scheme. So Donaldson-Thomas invariants, what Donaldson-Thomas invariant in general gives you some kind of number associated to moduli space of all possible coherent sheaves. But the one we are interested in connection to Gromov-Witten invariance, the ideal sheaf of curves. And that moduli space is the Hilbert scheme. Now you will see that even computing Donaldson-Thomas invariant is not exactly giving you the number of counting curves that you want, because you would realize Hilbert scheme is not exactly parameterizing curves, but is parameterizing curves and some extra structure attached to the curves. And those are the reduced structure of the curve, scheme theoretic reduced structure attached to it. So it's not like naked curves, it's some kind of a curve with a bunch of points on it, maybe a bunch of points off the curve. It's a bizarre situation. So this is basically, I'm telling you this because this story has survived to be interesting because of such technicalities. Like Gromov-Witten numbers are not exactly counting something, but Donaldson-Thomas invariants are counting something, but that something is not a naked curve. It's a curve with some cloud of points on it and off of it. So many conjectures are around these theories and around how to clean up these theories, really. How to clean this up, really. We will discuss it. Then there is Ponter-Banda-Thomas, stable pair invariants, blah, blah, blah. Okay? Did that answer your question?
Yeah.
All right, good.
So I just looked over the Donaldson-Thomas invariant, and So I didn't read the details, but I want to ask you. So when we consider the modular functor of it's a stable sheaf or a semi-stable sheaf, which is in the frame of a Donaldson-Thomas series. So so we know that in the Gromov-Witten series that if we replace a base field by the, so in that field, so let's first consider the base field is C. So in that case, it's the same as the Gromov-Witten environment. The modular functor is a DM stock, right? So how about in the Donaldson-Thomas series? How about in that side? It's a still DM stack?
No. So it's not a DM stack. It's an Artan stack, because in Donaldson-Thomas theory, the one that we will be studying is parameterizing ideal sheaves. Ideal sheaves are automorphic to each other modulo multiplication by C star.
Okay.
So a stack of this thing has the group of infinite order group of, I mean, how many elements are there in C star? Infinitely many. So it's an Artan stack, but that's fine. The coarse underlying moduli space, because of the stability condition, the coarse underlying moduli space is a scheme.
Okay.
So, and a scheme is a special case of DM stack.
Okay.
That's actually a fine moduli space even. So automorphism group of these things, because we are just counting the stable sheaves, is going to be even given by identity. And that's why in the number calculation, you will have some number dividing by order of the automorphism, which is 1. So you don't get rational invariance.
Okay. Okay. So is there any possible to consider this case over the base field as positive characteristics? Do you know anything about this?
About what? Consider
over the base field is positive characteristics. The reason I'm thinking about this question because I just look over the paper by the Kahler and he studied the theory, yeah, by the microlocal geometry. But and in that side he used characteristic cycles in a sense of a Kashmara, and but we know that there is a series which is constructed by Bellison, and he constructs a correspondent part for the characteristic cycles in the algebraic part. And what I want to do is to try to, if I can use something, the skeleton which is constructed by Bellison and Takashi Saito, so to study the, but their case is pure algebraics and over the étale topology. Yeah, this is what I'm thinking about.
Yeah, I have not, I should look at that paper. I have not ever seen calculation of these things over positive characteristic, to be honest.
Okay.
And it's only because over the positive characteristic, the whole notion of the even topology of the moduli space kind of changes.
Yeah, because in the Gromov-Witten series, if we replace the base field by the positive characteristics, and I read some paper, they said, okay, so that moduli stock is not DM stock anymore.
That's right, probably. Yeah. Yeah, then I don't know.
Okay, thank you.
No, and I haven't seen that. Yeah, but that's a very good question. Yeah. Okay.
Thank you.
All right, fantastic. See you guys same time Wednesday.
Yeah.
See you. Bye.
See you.
All right. See you guys. Bye.